Next, we want to look at the theory of plate tectonics, which is the unifying theory that explains the dramatic changing surface features of the Earth.
Now, in this theory, the Earth's lithosphere is divided into 8 large plates and some smaller ones, and the continents move because they are embedded within these drifting plates. So again, the plates, these are sections of the Earth's strong, rigid outer layer, the lithosphere. And the plates consist of uppermost mantle and overlying crust, and plates overlie and right atop the weaker asthenosphere. So here we see different plates noted in different colors. So you can, for example, see this kind of brown plate. Look at what's on this brown plate. This is North America, and then you have this purple plate here where we can see South America, and there's this kind of orange plate where Africa is embedded in. So these different plates have the continents embedded in them, and these plates are moving relative to one another. There are 8 major lithospheric plates, and these plates are always in motion and continually changing their shape and their size. The largest plate is the Pacific Plate, and several plates include an entire continent plus a large area of seafloor. Now, the different plates that make up the Earth's tectonic plates, they move in different directions and in different speeds. Continental plates tend to move more slowly. Oceanic plates tend to move more quickly. So let's do one of these check our understanding quizzes. The question is, continental plates tend to move more slower than oceanic plates because, and our options are, their roots extend deep into the mantle, they are heavier, they are convergent, or because of gravity. And I think if you think about it, you might guess that the right answer is that the roots of the continental plates extend deep into the mantle. Remember, we talked about the crust of the ocean is very thin, and then you have the place where the continents and they extend much deeper into the mantle. And so these guys are going to be moving much more slower than these guys just because they're so much more massive. And because they extend deeper into the mantle. And so they're more difficult to move than the thinner oceanic plates. Now, the theory of plate tectonics indicates to us that interactions between plates occur along boundaries of plates. That is, where two boundaries of two plates are side by side. And there is creation and destruction of the lithosphere, which occurs along the plate boundaries. And earthquakes, volcanoes, mountain ranges, these things occur along plate boundaries as well, and sometimes along former plate boundaries. Now, there are some different kinds of boundaries that exist among the tectonic plates. There are divergent, that means separating, spreading apart. They're diverging plate boundaries. And these kind of boundaries have magma generation and lithosphere formation. They're what are called convergent plate boundaries. Convergent means converging or coming together. And here again we have magma generation, but we have lithosphere destruction. And so we have either the creation of new lithosphere or the destruction of lithosphere. And then there's another type called a transform fault boundary. Here we have no magma generation and no formation or destruction of the lithosphere. So let's look at the divergent boundary plates and see how they are. So I've got a plate here and a plate over here, and there's a gap between them. And these guys are experiencing pressure from underneath that's driving them to separate. And so the plates are going to move away from one another. As they move apart, asthenosphere rises and partially melts to form lava. New crust is formed as lava fills in the gaps between the plates. So as these plates separate, it creates a gap. Lava comes up from underneath and cools and solidifies. In the ocean seafloor, in the ocean, this causes seafloor spreading, and this is particularly pronounced along the mid-ocean ridge. On land, continents tear apart because of this. There's a rift valley, and this kind of process causes shallow earthquakes, earthquakes that don't go very deep into the interior of the earth. Now, another kind of boundary layer is what's called a convergent boundary, and that's when the plates are coming together. So here you have a plate and another plate, and they're pushing together, and you can see what's happening is this plate, as they're jammed together, one of them gets forced underneath, and the other one slips and is pushed on top. And as this guy is driven down, you have sort of destruction of that crust. So that crust is sort of broken away. And so again, with convergent boundary features, the plates move towards each other. You have destruction of the oceanic crust. The continental crust is deformed, and this creates deep earthquakes. You can see this is being driven down into the interior. That causes deeper earthquakes. And this kind of convergent boundary is particularly pronounced when you have two oceanic plates converging. So remember, we have continental plates, which are deeper, and we have oceanic plates, which are thinner. And when the two oceanic plates converge, the older and denser plate tends to descend beneath the other. This process is called subduction. And as the plate descends, there's a partial melting of the mantle. It generates magma and volcanoes. If volcanoes emerge as islands, a volcanic island arc is formed. Japan, the Aleutian Islands, the Tonga Islands, these are examples of the result of this kind of process. Now, another kind of convergent boundary is what we call an oceanic continental convergence. That's where you have an oceanic plate and a continental plate coming together, converging. And when that happens, the denser oceanic plate subducts beneath the less dense continental plate. In other words, the ocean plate is the one that goes underneath. And as the plate descends, there's a partial melting of the subducting rock that generates magma. This tends to produce mountain ranges by means of volcanic activity from the subduction of the oceanic lithosphere, and compression from convergence are called continental volcanic arcs. The Andes and the Cascades are examples. And then the next example, we have a continental-continental convergence. That's two continental plates coming together, and the continued subduction can bring these two continents together. The less dense, buoyant continental lithosphere does not subduct. The result is a collision between two continental blocks. And this process produces mountain ranges like the Himalayas, the Alps, the Appalachians, etc. Now, when we're looking at the continent-to-continent collision type of convergence, an example of this was with India and Asia, and that produced and is still producing the Himalaya mountain range. And so the Himalayas are caused by this kind of convergence. And so basically what you have is you have these two continental plates, and they are moving towards one another, they're converging, and it creates what we call uplift. And so these plates, as they get pushed together, the forces lift them up, and that's what creates these mountain ranges. And of course, this can be regions where we can see some of the deepest and strongest earthquakes. Now, another kind of boundary we have is the transform plate boundary. And here we have plates sliding past one another, and that means that no new lithosphere is created or destroyed. Most transform faults join two segments of a mid-ocean ridge, and the transform faults are oriented perpendicular to the mid-ocean ridge. This permits plates to move from offset ridge segments. So this also creates shallow but strong earthquakes. Now we have a classic example of a transform fault boundary that's very famous, the so-called San Andreas Fault, which you guys know is in California. And so these two guys basically are pushing to create sort of a side-to-side motion, and that slipping is what causes earthquakes. Now, most of these kinds of boundaries occur within ocean basins, but a few transform fault boundaries, such as the San Andreas Fault, cuts through the continental crust. So you can see this one's cutting through the continental crust here, but not all of them do that. Now, there are three types of stress caused by interaction between plate boundaries. There is compressional stress, where the slabs are pushed together. There's tensional stress, where the slabs are pulled apart. And there's shear stress, where the slabs are both pulled and pushed. That creates a sliding motion. So we can look at how rocks respond to stress in the three main ways. There's elastic deformation. That means it returns to the original shape. There's brittle deformation, where they break. And then there's plastic deformation, where there's kind of a flowing. Again, we can sort of think of our silly putty analogy to kind of understand how rock can flow. Now, this plate tectonic model accounts for the global distribution of earthquakes, and about 80% of the world's big earthquakes occur in subduction zones in a region called the Ring of Fire. An earthquake can occur either on or between plate boundaries. Strain begins at a depth as an elastic depth formation, and when the buildup of stress exceeds the rock's elastic limit, the rock breaks. This is how a fault forms. Now, how do we measure earthquakes? We use something called the Richter scale, and the magnitude of the scale measures the energy released in terms of the ground shaking. It's based on something called a logarithm, which is a way of dealing with very large numbers. And the logarithm of the amplitude of the waves, that's the size of the vibrations of the wave recorded by a seismograph. And basically what it means is a 1 unit increase on the Richter scale is a 10-fold increase in amplitude. So when you hear on the news that a 7.4 earthquake hit somewhere, an 8.4 earthquake would be 10 times as powerful or 10 times as big of vibrations. And so if you go from 5 to 6 magnitude, that's a 10-fold increase. If you go 6 to 7, that's, again, you're going up by 1. And so that means you have a 10-fold increase. Now, there's another scale called the moment magnitude scale, and that measures the energy radiated from the earthquake's focus, where the earthquake occurs. And for each 1 unit increase in magnitude, the seismic energy released by an earthquake increases by 30 times. So these scales are ways of dealing with very large variations in magnitudes of vibrations. Now, another thing that's associated with earthquakes are giant tidal waves, which are also called tsunamis. And a tsunami is basically a giant sea wave or a series of sea waves generated by a powerful disturbance that vertically displaces the water column. And so a reverse fault earthquake thrusts the seafloor upward, and that creates a huge displacement of water, and that generates the wave. And so that's why very often when you hear that there's been an earthquake somewhere in or near the ocean, you'll hear that there's a tsunami warning, that there's dangers of tsunamis being generated by those earthquakes.